Alright guys, so here is the second video for our Flip the Classroom lesson. In this video we're going to be talking about proving trigonometric equivalency statements. An equivalency statement is really just two trig expressions that we're saying are equal. And what we're going to be doing here is showing that the two trig expressions are equal by taking a step-by-step process by which we show how one side of the equation is obtained from the other, right? So we're going to start with one side of the equation and manipulate it with cancellation and substitution and show that it equals the other side of the equation. So we're going to choose one side of the equation to work from, and we're going to let the other side of the equation be our target expression, or the expression we're trying to get to. So right here, if I'm looking at A, generally I want to start with a more complicated side of the equation. So I would start with my first side of the equation here, and that means that cosine theta times cotan theta is the target expression, the expression I'm trying to get to. So right here, immediately, I know that I want to get rid of my subtraction, right? Because in my target expression, I'm seeing only multiplication. So I'm going to try to basically use a Pythagorean identity at some point. But I'm stuck because I can't use any of the Pythagorean identities because I don't have square trig functions for one thing. And cosecant theta and sine theta aren't related with a Pythagorean identity anyway. So in general, my strategy might be to change everything to sine and cosine and sort of see what I can get, right? So if I change this expression to terms of sine and cosine, I can say that cosecant of theta is equal to 1 over sine theta, and then that's minus sine theta. Now I can get one fraction term by getting common denominators. So right here, if I multiply sine theta by sine theta over sine theta, right, I'm going to get 1 over sine theta, and then right here minus sine squared theta over sine theta. And right here, I can bring these two fractions together since they've got common denominators. So I'll go ahead and do that. And that will give me 1 minus sine squared theta over sine of theta. And right here I'm pretty close because I know that 1 minus sine theta I'm going to be able to use my first Pythagorean identity to substitute for. So right here I've got cosine squared theta plus sine squared theta. Oops, let's write that legibly. Equals 1 as my first Pythagorean identity. And if I subtract sine squared theta from both sides, I can say that cosine squared theta equals 1 minus sine squared theta. So I'm going to be able to substitute cosine squared theta in here. I'm going to go ahead and do that, and that'll give me cosine squared theta over sine of theta. And now right here, I've got cosine squared theta over sine of theta, and I can start looking back to my target expression. I've sort of simplified my expression down here, and now I want to think about how I can mold this to my target expression with some substitution and manipulation here. Well, right here in my target expression, I'm multiplying cosine theta. So if I factor out a cosine theta from the numerator, I've got cosine of theta times cosine of theta over sine theta. And cosine theta over sine theta is cotan theta. So there I have it. There's my target expression. Right here we've got cosine of theta times cotan of theta, because we know that cosine of theta over sine theta equals cotan theta. Now right here, what I want you guys to do is try these next two. Again, I think changing everything to terms of sine and cosine is a good strategy to start out with if you can't see anything. Right here, one thing I would point out is that we can't use the Pythagorean identity with this one either, even though we've got squared trig functions, because cotan and cosine are not related with a Pythagorean identity, so you want to watch out for that. And then go ahead and just give these a shot, and we'll look at the answers together in a second. So pause the video and give these a shot. Okay, so starting with B, right here what I would say is obviously our left side is our more complicated side, and 1 should be our target expression here. In a lot of ways, if we simplify down our left side, we should end up with 1. So in general right here, we're kind of stuck. We've got two fractions that don't have common denominators, right? We could work to get common denominators, but one of the things that might work out for us is if we change everything to sine and cosine, we might be able to simplify these two fractions down separately, right? And then see if we get common denominators anyway, or if they simplify the denominators away. So right here, changing everything to sine and cosine, we get cotan squared as cosine squared over sine squared, and secant squared as 1 over sine squared. We get tan squared as sine over cosine squared, and secant squared as 1 over cosine squared. Now right here we are dividing by fractions, which is the same as multiplying by the reciprocal. So for both of our terms individually, right, we can take this division of a fraction and make it a multiplication of the reciprocal. That's going to give us cosine squared over sine squared times sine squared. And there our sines cancel, and we get just cosine. And right here with our second term, we get sine squared over cosine squared times cosine squared. And the cosines cancel, and we just get sine squared. So now we're left with cosine squared plus sine squared, which is the first Pythagorean identity, and that gives us our 1. For our second proof, we've got one that's a little bit trickier. Right here, it's actually a lot more like that first problem. So right here we've got cotan squared theta minus cosine squared theta, and we want that to be able to equal cosine squared theta cotan squared theta. So right here, again, we'd start from the side that has sort of some addition or subtraction that we're going to have to get rid of. And when we simplify, we should be able to sort of get that simplified statement to equal this if we can get rid of that subtraction. So right here, these guys aren't related with a Pythagorean identity, so I'm going to change everything to sine and cosine and see what I get. Right here we've got cosine squared over sine squared for cotan squared, and minus sine squared, or rather cosine squared. And right here, if we multiply by sine squared over sine squared, we're going to get common denominators. So that'll be cosine squared over sine squared minus cosine squared sine squared over sine squared. Now right here we can bring these two fractions together with common denominators, and that's cosine squared minus cosine squared sine squared. Now right here cosine is a multiple in both of the terms in our numerator, so we can factor it out, and we're going to be left with 1 minus sine squared theta, which equals cosine squared theta, right? If we manipulate that first Pythagorean identity, we get that. And then right here we're going to have cosine squared theta times cosine squared theta over sine squared theta. And from here, if we factor that cosine squared out of the numerator, which if we look back to our target expression is one of the things we're going to need, we're left with cosine squared over sine squared. And cosine squared over sine squared is cotan squared. And that gives us our target expression. Now, one thing I would say is there's lots of different ways to go through these guys, so don't feel like the way that I did it is necessarily the right way. If you got to the target expression through some other means, your math might be just as good. You just want to make sure that you're following the rules of algebra that you know from just simplifying expressions with variables. Okay, so we're going to talk about one other strategy that we're going to use for proving equivalent statements with trig expressions. And that strategy is basically going to be using the difference of squares. Now right here, when we have something like a plus b, we know we can get difference of squares if we multiply by a minus b, right? And that's a subtraction of two squares. Now, since all of our Pythagorean identities involve squares, that can be pretty handy for us. So right here, if I'm looking at an equivalent statement like secant theta plus 1 over tan theta equals sine theta over 1 minus cosine theta, I can sort of say, well, look, I can't really do anything with the Pythagorean identity immediately for secant theta plus 1 because secant isn't squared. But I could get that secant squared and have it subtracted from 1 if I multiplied by that a minus b, or secant theta minus 1. And now right here, if I multiply in the numerator, I've got to multiply in the denominator, right? Because I've got to multiply by something equivalent to 1. Now at this point, I'm going to have secant squared theta minus 1, minus 1, over tan theta, tan theta times what? Times my secant theta minus 1. So tan theta times secant theta minus 1. Now right here, I can use the Pythagorean identity, or a manipulation of the Pythagorean identity involving secant. We know that 1 plus tan squared theta equals secant squared theta. So if we subtract 1 from both sides, we know that tan squared theta equals secant, rather. So go back and do this again. Tan squared theta equals secant squared theta minus 1. And so right here we can plug in, or substitute rather, a tan squared theta. Come on. For our secant squared theta minus 1. And that's over tan theta times 1, secant minus 1. Secant theta minus 1. Now right here, I'm going to be able to cancel one of my tans out in the numerator. And I've got tan theta over secant theta minus 1. Now this is a tricky proof because we still don't have our sine theta over 1 minus cosine theta. But one thing we can do here is change things to sine and cosine and see if we can't get there, right? So in my next sort of series of steps, I can change tan to sine of theta over cosine theta, and that's over, and right here we can say that would be 1 over, and then this would be cosine theta minus 1. Now right here I can get common denominators by changing 1 to cosine over cosine. And now right here we've got sine of theta over 1 minus, sine of theta over cosine of theta. Over 1 minus cosine of theta over cosine of theta. Now by multiplying by the reciprocal, we can say that we've got sine of theta over cosine of theta times cosine of theta over 1 minus our cosine of theta. And right here we can cross cancel, and we get our sine of theta over 1 minus cosine of theta, which is our target expression. So again, it's a process by which we sort of simplify. I know that I need to get my 2 terms in the numerator to be 1 term, and I can sort of get there with a Pythagorean identity, which I've got right there. Now I've got, and when I simplify after that, I've got 1 term in the numerator and 2 terms in the denominator, which is a lot closer to where I want to be. And so basically at this point, I can change things to sine and cosine and sort of see what I get. All right, so we want to look at another example where we're going to be using this method of multiplying by those other 2 terms that will give us difference of squares. Right here we can see how that can help us in 2 ways. Right here we're saying that the sum of these 2 fraction expressions is going to equal this single term expression on the other side. Immediately right here, I know that I want 2 things. I want common denominators, and I want 2 terms to become 1 term, right? So right here, what I want us to do is pause the video and multiply by the thing that's going to give us difference of squares over itself for both of these fractions. So we're going to pause the video and do that. Okay, so right here, I've multiplied 1 over secant x plus tan x by secant x minus tan x over secant x minus tan x. And that's going to give me difference of squares when I multiply the denominators, right, which will give me a Pythagorean identity, I hope, right? And right here I've multiplied 1 over secant x minus tan x by secant x plus tan x over secant x plus tan x, which should also give me difference of squares in the denominator, and subtraction of 2 squares, which could potentially give me a Pythagorean identity. Now, if we're saying these things are true, In general, the strategy we're using should work to help us consolidate our two fraction terms down to one term. So what I want you guys to do is to go through the rest of this proof by multiplying your fractions in green parentheses here and getting common denominators, bringing those two fractions together, and then just simplifying it down to our 2 plus secant x. So you guys should be able to sort of handle the rest of this proof yourself. Pause the video and give this one a shot. Okay, so here's the rest of the proof. We multiply out those fractions in green parentheses, and we get secant x minus tan x over secant squared x minus tan squared x plus secant x plus tan x over secant squared minus tan squared, right? Now with common denominators, we can bring these two fractions together. We're adding the numerators. So right here we've got secant x minus tan x plus secant x plus tan x. Right here we've got a negative tan x and a positive tan x, so those guys are going to cancel. Right here we can say we've got two secant x's, right? Remember, we're adding them, so that means we're going to have a coefficient of 2. We're not multiplying them, they're not squared. And right here in the denominator, we've got secant squared x minus tan squared x. And if we manipulate that second Pythagorean identity by subtracting tan squared x from both sides, we get 1 equals secant squared x minus tan squared x. So that gives us 2 secant x over 1, or just 2 secant x. And that is our target expression. So that's the proof portion of the video. Right here we're going to call this one, and I'm going to make one more video, and we may try to put that one on this too. We'll see how it goes. All right, so you'll see the videos that are up, and just look at the ones that are up and match those with the notes. All right, guys, see you Wednesday.